Hello, this video is on what happens when tectonic plates collide. A lot to get done on the plan, but the main idea is that we're going through what happens when the different types of boundaries collide. Ocean with ocean, and continent with continent. There's a fair bit down here for you to be successful. You'll be able to do these things. I'm going to come back to that, but it will mean that this video doesn't quite get you 100% around them, but it's a good place to start. Number one, what happens when oceanic and continental collide? So I'm going to use the word here, converge. To converge means to come together. So just to make sure that everyone's aware of that language, converging boundaries are ones that come together. So here's a picture I found. It's not a very good picture, but it does show that they're converging, they're coming together from either angle. And what happens is the oceanic crust dives down or gets forced down underneath the continental crust. And I like to imagine that as if a motorbike was going to hit a bus head on. The motorbike is going to end up underneath the bus because it's smaller and it gets wedged underneath. That's pretty much the same idea. The oceanic crust, which is thinner, goes underneath the continental crust when it hits. This is a not terrible diagram of one that a Year 9 student has made for me, and they've made it into an animation. So you can see that the crust there is diving below. When it gets down there, it melts, and that forms a bit of a volcano. And that's pretty much the story summed up very quickly there for you. And this is the diagram that we need to be able to draw to show that. So let me go through. First of all, we have this here, which is our oceanic crust. I'm going to colour that all in red. And we have the ocean, which is blue, and it's sitting over the top of the oceanic crust. And because this is land, I'm going to colour that the closest thing I can get to brown. And that is our continental crust. So let me label them. And of course, underneath the oceanic crust, we have the asthenosphere, and I have marked the convection currents that go around in a circle there. So let me label that. And we start to get a pretty nice looking picture. And I can draw in some clouds and some birds. And voila. Now, you might be thinking, yeah, okay, I can see how this plate is moving down and that plate is moving across. But what is the rest of the stuff that is happening here? Well, on the bottom of the ocean floor, you have a heap of sand and sediment. And when that actually comes up against this continental crust here, it gets scraped off. So we call that an accretionary wedge. But not all of it gets scraped off. You also have some parts of it that make their way with the crust all the way down to there. And not only some sediment, you also have parts of water, because the whole thing is wet, and that makes its way all the way down there too. Now it's important to stop and say, down where? Down here in the asthenosphere. It's quite deep, so there's a lot of pressure, and it's quite hot. So I draw X's here, and I have to label those X's, otherwise they don't mean anything. And I label them melting, because that's what happens down there. What is happening is that we have oceanic crust, water, and some sediment all melting together. And of course, hot things rise. So I'm going to colour in my magma plumes. And they're moving up because they're hot. And eventually, over time and time again of this upwelling magma, you form a mountain, you form a volcano. At the very least, there's a mountain because it gets thick. At the most, you end up with a volcano coming lava out the top. It's not a very good explosion. Excuse that, I'm going to do a better one. Yes, you're right. That's not much better. Still, let's move on. Okay, what does that tell us about the rocks? And what does that tell us about the nature of the volcano? Question mark. The rocks formed. I'm going to keep this simple and not do much writing, so I'll do the talking here, and I'll leave it to you to get this down in your own words. What we have here is the melting. And what is melting? You have some oceanic crust, you have some water, you have some sediment, and because it's hot, you also have the partial melting of some continental crust. Now the reason why that continental crust melts is because this water here actually acts on the continental crust in a bit of a strange way, and that lowers its melting point. So what that means is that you have some unholy mix of all of these rock minerals. Some mafic, oceanic crust, some dense mafic minerals melt. You have some sediment, so a lot of things that die and form underwater, so some limestone and some sand and stuff. And you have some continental crusts, which are largely felsic. What happens then, guys and girls, when you mix mafic with felsic, and they all mix together and form a lava, is you get an in-between. You get an intermediate type of rock. And that is literally a kind of rock. It's halfway between mafic and felsic. It has an intermediate number of minerals or mix of minerals in there. And importantly, it has high to moderate concentration of silica. And of course, silica is what gives the felsic the sick. It's what makes the rock lighter in colour and less dense, generally speaking. And an example of an intermediate rock that I'd like everyone to remember that is formed in this sort of boundary is andesite. Largely an extrusive igneous rock, intermediate mineral composition. You can see it's got a grey colour there with visible spots. I don't think it's crystals though. Why this is important? A lava that has a high concentration of silica is very viscous. That means it's not runny. It's very heavy. It doesn't flow like peanut butter. You couldn't pour peanut butter out of a jar. And likewise, you couldn't let this lava flow freely. So I'm going to write here doesn't flow. And what happens then is it doesn't flow, which means it doesn't relieve any pressure. And that means, guys and girls, pressure builds up and you end up with a very large, explosive and dangerous volcanic eruption. Kaboom! Whew, that was exciting. Number 2. Oceanic versus oceanic. Now, I'm not going to write so much about this one because it is pretty straightforward. Instead of the last one, where it was oceanic continental, this time it's just oceanic with oceanic. So you have oceanic coming there, oceanic coming in there. One goes down because that one's just the more dense, or the thinnest, or the coldest, and it goes down and subducts. And it's pretty much exactly the same as last time. You have, you have a melting upwelling of magma, and then that forms a little bit of a mountain range. However, this mountain is underneath the ocean, so it looks like an island. And what happens is you end up with a whole lot of islands that pop up down the ocean. And they look like a bit of an arc, so we call this a volcanic island arc. So if you're looking at a map and you see a volcanic island arc, that's a pretty good indicator that you're looking at an oceanic and oceanic convergent boundary. Now, these convergent boundaries aren't so explosively eruptive. I don't know if that's a word. The eruptions aren't as explosive. The reason is because you've got 2 oceanic crusts coming together. Both of them are mafic. Mafic and mafic melting together is only going to give you mafic lava. Mafic lava doesn't have the silica content, and therefore mafic lava flows. These eruptions are quite peaceful, just like the mid-ocean ridge eruptions. A type of rock formed here, just like at mid-ocean ridges, would be basalt or gabbro. I'm feeling very lazy, so I'm not going to label this diagram, but it's something like you should be able to draw for this too. Oceanic, converging, which means I do need to put my arrows in. Then I have my melting down here, plumes of lava rising up. This time the volcano here only pops its head above the ocean, and we end up with what looks like an island. Last but not least, number 3 is continental versus continental crust. And let's be honest, everyone, this one is even easier than the other 2. You end up with 2 large, thick pieces of continental crust butting heads and coming together. What happens? Because no one is dense and no one is thinner than the other, you end up with just a bit of a butted head. Both of them don't break the other one, both of them don't subduct the other one, they just sort of butt heads, and over time the butted head section gets bigger and bigger and bigger, It would be as if you took two bits of Play-Doh and smooshed them together in different directions. One coming in here, one coming in here, and you end up with some sort of giant fold. This is literally a fold mountain. And it's because of the convergent pressures, and because both crusts are equal thickness and equal density, they don't subduct. They call them fold mountains because they literally fold the rock and it goes up. An example here is Mount Everest. Everest is caused by the Indo-Australian plate pushing up into the Eurasian plate. It's not going to stop, it's still moving up there. So every now and then they get this big earthquake which releases all of the strain, and there's a bit more folding, and the mountain seems to have grown another metre or two. It's going to keep on getting taller. There are no rocks formed here because there's no melting. So that one's pretty easy, but there are a large risk of earthquakes. And that brings us to this overview's end, guys and girls. We've done oceanic, continental, oceanic versus oceanic, and continental versus continental. So in your books, everyone, you need to be able to go back and do 3 pages. First page, you're doing oceanic versus continental, and then second page, you're doing oceanic versus oceanic. Third page, you're doing continental versus continental. Now, for each of those, you need a diagram, please. Ruler and pencil, make it half a page big. You need text to describe what happens in each place. For these two, where a plate subducts, I want you to write the definition of subduction there. And geological features is something that we're going to talk about in another video or at class at some point. For these two, again, you need to be able to name rocks formed at those boundaries, and you need to outline why each type of eruption is explosive or peaceful. Just to give it away, this one here is explosive because of the silica content of the magma. This one here is peaceful because the magma doesn't have that silica content and it can flow. It's very important you can articulate that in your own words, and the diagrams need to be very good labelled. And go back and look at my diagrams too, and do a better job of labelling than me. This is only an overview, guys and girls. This is going to take some more time and some work in class, but this is a good starting point and a good place to return to if you are getting stuck on some of the bigger picture details. Thanks all. Bye.